Welcome back. In this lesson, we're going to look at the largest group of rock-forming minerals called the silicates. And silicates are simply made of two elements, silicon surrounded by 4 oxygens. It makes a pyramid shape. And so those pyramid shapes can either by themselves become minerals or link up to form different 2- and 3-dimensional shapes of simply combining these groups of little pyramids. And this is called silicates. And there are about 90% of the rocks on Earth are made up of these silicate compounds. So it's a very beneficial and useful part of our time to look at these and how the geometries of them and these different groups of them that make up so many of these rocks. It's very scary. Geology is scary to a lot of people because there's so many minerals. There are many, many thousands of minerals, but there's really only just a few that is the main ones. So you do have very rare cases, lots and lots of rare cases, but the majority of minerals, there's only a few dozen, and that's learnable by anybody. We're just taking an overview of geology, so we're going to look at the big ideas, but these minerals are known as rock-forming minerals because when you look at the rocks on the Earth, most of the rocks on the Earth, a great percentage, is made out of these silica tetrahedrals. You can see that some of these minerals are economic, meaning you can mine them. You can mine salt. You could mine different kinds of ores, which are minerals. And you have very common rocks that people would just leave on the ground if they found it. These minerals are mostly made out of just a few elements, and silicon and oxygen being the greatest, because if most of the rocks are made out of rock-forming minerals that are silicates, then most of the rocks will be made out of silicon and oxygen, because that's what a silicate is, silicon and oxygen. All of these other trace elements are found in minerals, and you're going to have different types of minerals. You can have potassium minerals, you can have iron containing minerals, and a number of others. But the great lion's share of rocks on Earth are made out of silicon and oxygen. We're going to see that these tetrahedrons that are made up of the silicon and the 4 oxygens can be linked together, and the various minerals can be made out of this. You can have up to 800 different types of minerals. You'll have classes of minerals or big families of minerals where you'll have basic commonalities, maybe replaced with one element instead of oxygen would be replaced for something, or something inside almost like a pollutant. But in any case, you really only have a few major groups, and they do make up almost all of the rocks on Earth, 90%. I got out my toys to show you how to build a silicate. We're going to see that the rocks on the Earth, most of the rocks on the crust of the Earth, are made up of silicates, and silicates have 2 elements in them. Silica we're going to represent with the black ball, and oxygen with the red ball. You can see that silicon is going to have 4 hands, so each of these arms are going to hold a double electron. So we have a bond here. This is sharing a double bond, or sharing a single bond. That's one bond, 2, 3, 4. So there's 2, 4, 6, 8. Silicon has 8. That's the octet rule, so it is stable. Oxygen, we're going to see, is not exactly stable. It has 2, 4, 6, 7. This is an open space, and each of these oxygens can, for that reason, hold hands with something else. It can either acquire hydrogens, or it can link up with other elements or with other silicon tetrahedrals, because what the shape is going to be, a single shape, is a tetrahedral. So a tetrahedral is 4 that are trying to get away from each other. Do you see there's electrons here? These electrons try to get away from each other, and because of that, they end up in a beautiful 3-dimensional shape called a tetrahedral. Anything can be the top. Okay, and no matter how you orient it, it's going to have the same configuration. Essentially, it's a triangle, okay, and there's 4 equilateral triangles that are making up a pyramid, so that's tetrahedral. So if I were to use this extra electron to form a bond with another like another tetrahedral group, then I could have a chain. Okay, so if I had a chain, you could just imagine a very long chain of tetrahedral groups. We'll look at a table in a minute to show you the different rocks that would be made up of singles or chains or cyclics or three-dimensional or sheets or three-dimensional groups. So each of these would have their own rock minerals attached to them. But in any case, and this is that extra electron that it can simply make a bond with another silicon and then form another tetrahedron. So this would be a tetrahedron, this is a tetrahedron, and so you have these pyramids that are forming one next to each other, and that would be it is three-dimensional, but it's more of a chain, so almost like a two-dimensional object. Okay. Now I've got here three-dimensional. Let me break it down just a little bit to make it easy, because you can see that it can just get very sophisticated very fast. Let me take this final row off. Okay, so I've showed you that you can make three-dimensional groupings. Okay, I don't want to break my things here, so. Okay. All right, so here, okay, let me go out a little bit. I can see the next one would be just one of these. Okay, this would be a cycle. So you can have a cyclic group to where instead of one tetrahedral, essentially you have three tetrahedrals, okay, because you have one here, one here, one here, going up at different angles and forming a cycle or a circle, okay? So that would be a cyclic. You have different, beryl, I remember, is a gemstone that's simply made out of lots and lots of these little cyclic tetrahedrons. Now, when you connect them to, so here's a strip, remember here's a chain, you attach the two chains together, and now I've got a sheet. Okay, so this would break apart right here. This would be a beautiful cleavage line. Like if you were to bring a knife here, it would simply pop these very easy, and this would just shear off nice and straight, and this would shear off nice and straight, and this can be as long as it wants, this could be as long as it wants. So it have strong bonds here. These bonds would be very strong. These bonds going to the next sheet would be very weak, and so when they split, they're going to split like sheets of paper. Okay, so one after next after next. By the way, your pencil lead works like this. That's why when you smear the pencil lead on a piece of paper, really it's almost like taking a deck of cards and kind of fanning the deck of cards so that one and then the next and the next and the next, and it fans across. That's what you're doing when you're drawing your pencil across the paper and making a mark. Okay, so you are shearing off these sheets and then the sheets stick to the paper. Okay, so review. You can have single tetrahedral groups, you can have chains of tetrahedral groups, you can have rings of tetrahedral groups, you can have sheets of them, and you can have three-dimensional structures on them. So here's an example of what I was talking about before. The single tetrahedra, which are those little pyramids, you can have minerals, and it's a whole group of minerals, but it's called the olivine group, and an example would be olivine. So it's a beautiful green kind of jade-colored rock, and it's made entirely of these little tetrahedra. So there's other ones. You can have different kinds of minerals interjected into those tetrahedra, but for the most part, pure silicate would look like that, just tetrahedral on their own. You can have an entire group. Remember, there's 800 of these. Okay, so there's lots of different kinds of minerals. The group that would be chains, where you have a single chain of them, are the pyroxenes, and so you have different types of pyroxenes. The example here is an augite, and this would be very difficult to memorize all of the types of minerals in this class, but once you have some idea that, oh, this is a chain, well, you can make predictions about how that will cut, what the crystal is going to look like, what the shape of the crystal is, whether it is in sheets or strips or links or whatever. You can make some predictions. So the next group, the amphifold group are in double chains. So I would interject one in here in between, and that would be like the beryl group, B-E-R-Y-L, which is a gemstone, and it would be a single ring. So you can see that a double chain is really a chain of rings. So as they come in from both sides and make a ring, and then you have a double chain, which is a linkage or a chain of rings. One ring would be a beryl, and then a double ring would be the amphifold. And hornblende, which is one of the elements inside quartz, is an example of a double chain. Then the next one is if you link these double chains together, you can get a sheet. So something that would peel off in sheets. And so these biotites or muscovite, little tiny, like little glass windows. They look like little pieces of thin glass because they break apart in thin sheets, and you can actually see through them. Then when you build three-dimensional structures out of these two-dimensional structures, you can have quartz, which a lot of people would be able to recognize quartz. You can have transparent quartz or smoky quartz or different kind of stains like rose quartz. And then another element, quartz is also in granite. And then the last one, which happens to be in granite as well, is feldspar. That is a silicate that's also three-dimensional. So these are the ones. To know this is to know 90% of the minerals that make up all of the rocks on Earth. So it's a good use of your time.